All right, here we are. Great. Thank you to everybody who has been waiting. I apologize. We had a Zoom blip, which happens from time to time. So thank you again for waiting. Welcome to this evening's Space Place Canada event. We are delighted to have you join us, and thank you again for waiting. My name is Kirsten Vanstone, and I'm a director at Space Place Canada. I'll be your host for this evening, and I would like to thank Gabriella and Arvind, who are behind the scenes and were troubleshooting rapidly to try and figure out what was going on. They will be monitoring your questions and comments tonight and making sure that everything runs smoothly. I am joining you today from the traditional territories of the Haudenosaunee Confederacy, the Huron-Wendat, and the Mississaugas of the Credit First Nation. This land is part of the Dish with One Spoon Treaty and is now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. You may be joining us from another part of Canada or even farther away, and I encourage you to learn more about the history of the land and peoples in your area. Just want to ask, did any of you see the aurora the other night? I didn't. It was cloudy here in Toronto, but my sister out in Saskatoon got some beautiful photos of it. It was amazing and just a once in a lifetime, maybe twice in a lifetime thing to see. And if you have ever looked up in wonder at the night sky, you will want to learn more about Space Place Canada. We are a Toronto-based not-for-profit working to reestablish a world-class planetarium in Toronto. This will be a strategic hub for STEM education and community inspiration. You can learn more about us at our website, which is simply spaceplacecanada.ca. We don't have a planetarium yet, so we'd like to run a few events like this every year as we work to realize our planetarium dreams. If you like this idea of a planetarium in Toronto, we would like to consider, or we'd like to ask you to consider remembering us in your year-end donations. We are a registered charity and will issue tax receipts for cash donations. Just want to mention Giving Tuesdays next week, so a week from today, so just saying, might be a good time to send that donation to us. But now I want to get on to the main event. Did you know that Canada does a lot of astronomy? You may not think of it, but in fact, in recent years, it has consistently ranked #1 in the world in terms of impact of astronomical research, and this is measured by citations of scientific papers. And if this came as a surprise to you, that's probably because of who tells the stories of scientific discovery, especially in astronomy, astrophysics, and space travel. And that is like people like NASA or the European Space Agency. There are so many firsts coming from Canadian astronomical research, and tonight's guest has been part of a lot of them. Mike Fick is Professor Emeritus at the University of Waterloo. He does a lot of research into stellar formation, dark matter, interstellar medium, galactic structure. He will tell you more about that. But he is also a telescope builder. And he was just telling us that he's been doing this for more than 50 years, which I admit, I'm quite impressed that you admitted that. Starting with his high school astronomy club back, I won't say how long ago. Now, telescope building has changed quite a lot over the last centuries. And in fact, in the last 100 years or so, the world's most advanced telescopes, a little bit probably more advanced than the one you built at school, they've been built higher and higher up, not just to get above the clouds, but to get as far above the blanket of air that is constantly moving around our atmosphere. This is the air that we need to breathe, but it kind of messes up astronomical imagery and observations. In fact, when the Lick Observatory was built outside of San Jose, California, it was actually a compromise to put it on low Mount Hamilton, which was 1,300 meters or 4,200 feet. The original plan was actually to put it in the high Sierras at 10,000 feet. But remember, back then, they didn't have cars to get stuff up the mountains. They had to use horse and cart and donkeys, and several of them, these animals did not survive. So it was quite extreme. But almost 140 years later, the race to the top continues, with telescopes being constructed in some of the harshest conditions on the planet. And tonight, Mike is going to tell us the story of the Fred Young telescope and why astronomers continue to go to such lengths to build these things that will help them understand the universe. Over to you, Mike.
Thank you, Kirsten. The opening slide that you're seeing here is actually a photograph from about 15 years ago of the site where we've built the Fred Young submillimeter telescope. And superimposed on here is an artist's picture of what we thought the telescope would look like when it was finished. As you'll see, it doesn't quite look like this. and it's not quite placed where we were originally expecting it to be, but that's for later in tonight's talk. Okay. What I'm going to talk about here is sort of a general plan of today's talk. I'm going to talk about submillimeter wavelength astronomy because this is a submillimeter telescope. So what is submillimeter wave? What is that kind of light? And what kind of science do you do with that? And I'm going to mostly talk about cosmology. In fact, half my talk is going to be about the science that motivates building this telescope and going to such extreme altitudes and difficulty to build such a telescope. I will talk briefly a little bit about some of the other things on here, but really I'm going to talk about cosmology. Then the big thing is the title of this talk was Very High and Dry. Why do we have to go so high and dry? In fact, it's the site that we found for this. One of my colleagues discovered about 20 years ago that this particular site that's now the CCAT Observatory is for this kind of astronomy, for submillimeter wavelength astronomy, this is the best place in the world to do this. The only way you could do better is to go into space. So I'll talk a little bit about why is that? Why is the site so important and what makes this site so special? Then I'll talk about the telescope itself, a little bit about the design, and then I'll start to show you some pictures of where we are today, the current status, and when we expect to be finished. And then finally, just a little bit at the end, there is a future beyond this. We have plans what we will do after we've finished the first 5 years or so of working with this Fred Young submillimeter telescope. So first of all, visible light. We all know what visible light is. It's the light that your eye can see. The other wavelengths of light, by the way, are not invisible light. They're just not visible is the correct way to call them. So the light your eye sees is light between purple light and red light, this whole range of things, the rainbow as we normally think of it as. And the usual way we describe light isn't by a color, it's by the wavelength. But this visible light is just a tiny fraction of all the light. But nevertheless, this is the kind of stuff here. These are the pictures we see. I'm just showing you flashing through a whole bunch of the pictures that we see with visible light. There's lots and lots to see. The pictures here, I went through, I'll do that one more time because I went through it really fast. There's a comet that's close. Jupiter, a little further. Star cluster, a galaxy, a cluster of galaxies, and a big part of the universe. And these are all visible light. There's a lot of data here, but still, it's just all visible light, although the Webb telescope on the right goes a little bit into the infrared. The infrared, well, here's visible light. Here's all the wavelengths of light. And you can see this little narrow bit in the middle is visible light, the light that our eyes can see. And at longer wavelengths to the right of the visible light is the infrared, and further to the right is radio waves. Your microwave oven, I've shown you somewhere in there. The vertical red line is 1 millimeter. So wavelengths of 1 millimeter, that's the critical wavelength for when we talk about submillimeter. That's slightly to the left of this red line, slightly shorter wavelengths, and slightly longer wavelengths to the right as well. We usually make our detectors work there as well. And so there's a wide range of wavelengths, and they all tell you something different. If you're looking in the sky, different kinds of objects emit at different wavelengths. So, we're used to doing visible light because that's what our eyes see, but it's not just that. If you ask, how do objects in the universe emit? The first approximation is that things emit because they're hot. And so here is the emission profile, a plot of the emission, and you can see I put it right in the middle there. Let's see if you can see my little arrow. Here is the whole visible spectrum. And things that are hot, like 6,000 degrees, which is the sun, sort of has a peak somewhere in the middle in the yellow. That's why our sun is yellow. But things that are cool, like a human body is around 300 degrees Kelvin, doesn't emit at all invisible light. We do not see human beings by their emission. We only see by reflected and scattered light from people. Humans are 310 degrees. If you're looking at the colder parts of the universe, the visible light doesn't show you anything. There's no emission at the colder wavelengths. And a lot of the universe is colder than 1,000 degrees, much colder. So submillimeter science is looking at these parts that are really the cold parts of the universe. And there's a lot of it. So the things I'm going to talk about in more detail are the Big Bang, that we think that the explosion that started everything. That's still a theory, but there's very good evidence for it. And we haven't been able to refute the theories about the Big Bang. There's also many things that produce submillimeter light because they're not yet hot. Before galaxies, before stars, and before planets actually form, they are large clouds of gas, and they condense. Gravity, their own self-gravity makes them condense, and they warm up as they condense. But it takes a while before they get hot enough to produce visible light. And so when they're in this cooler phase of actually producing things, like when you're making a new galaxy or a new star or new planets, they tend to produce their light in the infrared and the submillimeter. And so that's, if you want to study the formation of things, whether it's stars, planets, and the galaxies, or whether it's the formation of the universe and the Big Bang, as we'll see in a few minutes, submillimeter is where we study how things got started. So since submillimeter wavelengths are longer than visible light, the instruments and techniques that are appropriate for visible light aren't always appropriate, but it's shorter than radio wavelengths, where we're used to using antenna like satellite dishes. The submillimeter instruments use both kinds of techniques. They will use both visible techniques. There are, for example, lenses that we use, but we also have large dishes that look like satellite dishes. And so you should, expect to see, large mirrors and things like that. So cosmology, main science topic for tonight, the expanding universe. Here's the sort of the foundation of cosmology. Edwin Hubble in 1929 started looking at galaxies fairly close to our own galaxy, but in many, many different directions. And he was measuring the distances to these galaxies and the speeds that they were moving. And they seemed to be generally, almost all of them were moving away from us. There was like one or two out of the many dozens that he looked at that were not actually moving away from us. And the more distant ones were moving the fastest. And if you think about that, if you look in all directions and everything's moving away from you, then you're at the center of the universe because everything's moving away from you. But that's not true. We have a really common thing that we like to use as explaining cosmology to theorists, and that is the expanding raisin bread. So here's raisin bread. The top one here is the unrisen raisin bread, and before it started to expand, you've got your dough. And if you let it sit for a while, it will expand by a factor of at least 2 before you're going to bake it. And if you have some raisins in this raisin bread, the raisins are going to move further and further apart. So for example, if in an hour, which is the typical time to proof some bread, if you have raisins that were originally 1 centimeter apart, and this expands after 1 hour, this particular loaf of raisin bread you're looking at has expanded by a factor of 3 in size, which is big, more than my bread. And that means that the raisins are now 3 centimeters apart. But if you're the local raisin, the raisin that's at one end of that line right there, and you look at the other raisins and ask, how far away are they at the beginning of the time and at the end of the time? Well, the closest raisin to the local raisin was originally 1 centimeter away, and now it's 3 centimeters away. It's moved 2 centimeters in an hour. The next closest raisin is now 6 centimeters. It's moved 4 centimeters. 4 centimeters per hour is how fast it's moving. The next closest raisin number 3, is moving at 6 centimeters per hour. And if you were to plot those, you get the same diagram that Hubble got. That local raisin thinks it's the center of the universe because all the other raisins are moving away from it. The more distant ones are moving even faster than the closer ones. And so the local raisin thinks it's the center of the universe, but it's not. And that means, no, we are not at the center of the universe just because everything seems to be moving away from us. Well, if the universe is changing and increasing in size and everything's expanding, there's many, many questions. And I've just listed a few of them here. For example, if the mass would be a constant, then you'd think the density might be dropping. And was the universe originally 0 size at some point? And is the change always been the same? Is it always expanding at the same rate? If you look at things at the same distance, has it always been the same? And what did the universe look like in the past? If it was denser in the past, was it hotter? That's the sort of thermodynamics argument. And if it was hotter, how would that change things? And then, of course, there's the other side of this. How is it going to go in the future? What's the future of the universe? And you could keep going. There's so many questions you could ask. So here's a different kind of plot. Instead of plotting the velocity versus distance from us, the way the universe looks to us right now, we could ask, how has the universe changed with time to produce what we see today? So the vertical axis, the y-axis here, is the scale of the universe, which could be the size or the average distance between galaxies, or it could be 1 over the density to the 1/3 power. It's basically an equivalent scale. And so that's the universe getting bigger on going up. And to the right is time. And all we have is today. We have an observation today. As you can see on here, at some point, this is the current time. We can't see into the future at all. So we have no idea what's happening to the right. On the left, we could expect that at some previous time, the universe was moving at some rate that might be the same as today. The universe is constantly expanding and not accelerating. And it depends on the speed. We could ask, when was the beginning of all of this? It depends. If it's slowly expanding, then the starting time is far to the left, way over here, if you could see my cursor. If the universe is expanding quickly, then the universe started here, which is not so far back in time, and the universe is younger or not as old as way over here. So what does that mean for the expansion? Well, I said constantly expanding, but there is mass in the universe. So there's gravity in the universe, and gravity slows things down. And we're measuring the expansion by galaxies. So the galaxies should be pulling each other together. They should be slowing down. We should see the expansion of these galaxies and the universe slowing down, which means that in the past, the expansion must have been faster. Well, then you ask the question, how much mass is there? Is there enough mass to slow it down a lot? Turns out there's a lot of history to this. Going back to 1884, Lord Kelvin looked at stars just moving around in our Milky Way and asked how much mass is required to let those stars orbit. That's, again, it's the same problem. It's just gravity and orbits. It's not the same as the expansion of the universe, but it's the same problem. We have mass and that causes gravity, and it affects the velocity. It makes things accelerate around in orbits. And he found that there was not enough stars to provide the mass that's required for the orbits that we see. And he called this dark bodies. He said there might be, many of the stars might be too dark to see, maybe most of them, because that's what the numbers say. A few years later, Poincaré actually called this dark matter. He said it in French, matière obscure, but dark matter. And that's the origin of the term dark matter. So if you hear about dark matter and you think it's this new thing in cosmology, it goes back more than 100 years to Poincaré. And there's lots and lots of history. And I'm not going to go through all of these different measurements of dark matter close to us, dark matter around galaxies, dark matter inside galaxies, measurements of dark matter in our Milky Way. I did that with my PhD work. But all of these various studies seem to indicate that most of the matter that we need to produce the gravity that we're seeing is not known. We don't know what it is. And since it's unknown matter, the term for it, we've just carried on with Poincaré's term, we call it dark matter because we don't see it. But what is dark matter? And the answer is nobody knows. We have lots of ideas, but nobody knows. Now, if gravity is slowing the universe, then originally it was going much faster. The dark matter is slowing down the expansion. The universe was going faster. If you go back in time before even that, the universe is going faster. If you go back in time before that, the universe is expanding even faster because it's continually slowing down. So at the very beginning, when the universe was very small, it must have been very dense, and it would have been expanded at a very high rate, which to me sounds like an explosion, a small, dense, really, really rapidly expanding thing. And somebody at some point said, that's like a big bang. And I actually think the first person to say that was ridiculing the idea and didn't really take it seriously. But the Big Bang is the name we give for this start of the universe, if the universe started this way. If it started this way in an explosion, very, very dense and very, very hot, as it expanded, it would have cooled. And we could ask, how much would it have cooled? So let's just take another look at the same plot of the scale of the universe and time. And now, instead of having a straight line just showing the constant expanding universe, we put in a curve here to show that the universe is expanding, but it was expanding faster. In fact, it's the slope of that dashed line that is the speed of the expansion, what would have been the Hubble law back then. And we could do this a little bit more generally and look at a bunch of different versions. We can look at there's the orange line there, which is the empty universe, which we know the universe is not empty, but a constantly expanding universe. And if we have a little bit of matter in the universe, a little bit of gravity, then the universe is slowing down, but it won't slow down enough to stop expanding. On the other hand, if we have a lot of matter, and remember, this is today right here, if we have a lot of matter, then the universe's expansion will stop. Gravity will be strong enough to stop the expansion, and the universe will collapse again in what's sometimes called a closed universe or a bound universe. And between these extremes, there's a boundary here, the marginally bound universe, or sometimes called the flat universe. Which universe are we in? Because we're only here right now, seeing how the universe is expanding right now. How do we get more information about what kind of universe are we actually in? Well, it turns out there's a trick. On the left is our Hubble diagram again. And what's special about this Hubble diagram is that it's going to very large distances, much, much, much larger than Hubble ever looked at. And the straight black line here is the constantly expanding universe. But there's matter in the universe. And the diagram on the right says what happens if there's matter in the universe. Well, the universe, the curve, it's not a straight line anymore. In fact, if you look here, I've got the blue line up here, which is the universe that is this Hubble law that goes way up. Why would it go way up? Well, that's the universe that over here is going very, very fast at the beginning. The universe at very early times, very shortly after the Big Bang, was expanding very fast. The speed would be very, very large. These galaxies, if you could see them, how can you see them? Well, when we look very, very far out in the universe, we're also looking back in time, because it takes a long time for the light emitted by the universe back here to reach us. And so we can look back in time. We can't look back to the beginning, but we can look back quite a long ways. And we can see perhaps galaxies that are expanding here faster than they are today, which means on this Hubble diagram, they're above the Hubble diagram. So we would expect this to curve up, and the amount of curve up tells us how much the universe has slowed down. It tells us how fast the universe was moving far back in time. Of course, this is really distant universes. This is very tough work to do. And this particular problem has motivated many of the developments in building giant telescopes. One of the reasons to build really, really large telescopes is to be able to see the very, very faint galaxies that are very, very far away, and therefore showing us what happened far back in time. So we can look back in time, but it's really hard. Okay. But here's what we see with these new telescopes. Hubble diagram again. Again, this is velocity here. This is just a Hubble diagram, large distances. And this is real data. And there's been many galaxies found below the line. That does not exist. That if you go back, there are no universes here. That's universes up here. How can that be? How can things have been moving more slowly back at that time than the empty universe? This has led to a whole collection of models. So here are all kinds of different kinds of models of the universe that are all drawn out here, and including some that have no Big Bang, no start to the universe. And what's happening here is that something is making the universe going into the future accelerate. There's an acceleration term. The curve down is caused by matter producing gravity that causes the universe to contract. What makes the universe expand would be some kind of energy, and we don't know what it is. And in analogy to calling matter that we don't know what it is dark matter, energy that we don't know what it is, we call dark energy. We don't know if it's real, although we've just seen the evidence just now. There is something. So what is dark energy? Now, there's lots and lots of theories of dark matter and dark energy. There's hundreds and hundreds of theories, and we don't really have time to explore those today. But what's happened is people are trying to put limits on those theories. So one of the tools that we have is to look at the cosmic microwave background. When the Big Bang happened, the universe was very hot, very dense. The universe has expanded. It's now much, much cooler, but it hasn't got to absolute zero. None of the theories suggest that the universe would cool to absolute zero. That would take forever. So people have looked at the theory, and George Lemaitre was the first person to really look at this idea. He was doing it for something wrong, but he got a very nice mathematical theory, and people have taken his theory and used that to predict what the temperature of the leftover heat from the Big Bang would be today. And it turns out it's about 3 degrees Kelvin. Now, this was just an idea in 1948. And, as some people, just said, that's, nice theory, what evidence is there for it? And then in 1965, Arno Penzias and Bob Wilson found microwave emission coming from everywhere in the sky, from every direction, and they measured the temperature as 3.5 degrees Kelvin. And they got the Nobel Prize for this because this was the very first proof. Well, proof is the wrong word. This was the very first support for a prediction of the theory. The theory predicted the universe would be 3 degrees, and that prediction turned out they found the 3 degrees. I'll just mention that there was a University of Toronto professor who actually measured this in 1941, got 2.2 K, didn't know what he was measuring. He just noticed that in all directions, the universe was 2.2 K. Going to ask me questions about that later. It's an interesting sideline. Now, there's lots of ways to go and look at this, but big problem is that the Earth's atmosphere is not very transparent. And we'll come into that in some more detail in just a couple moments. The main way that we studied the cosmic microwave background is with a set of satellites. And the first of these was COBE in 1993. And this generated another Nobel Prize, and it found the temperature of the universe, looking in any direction you want, you could fit that black body Planck law that I showed you for the emission as a function of temperature earlier, back in like the third or fourth slide. You could fit perfectly to 2.728 degrees. Now, perfectly is never exactly 100% perfect. It turns out it was perfect to 3 parts in 100,000 being identical. This cosmic microwave background is identical in all directions, but your measurement isn't perfect to everything and to infinite number of digits. And in fact, when they did this very, very precise measurement, they found that there was actually a 3 part in 100,000 deviation in different directions. There were follow-up satellites, WMAP, which measured more parameters. The cosmology models at the time, that standard model that is around this time is what's now called the lambda CDM model. And it has a number of parameters, one of which is the temperature of the universe, but also there's the age of the universe to put into this. There is a question of how much dark matter is there and how much dark energy is there. And is the universe open or closed? And WMAP showed that the universe was actually flat. It's right on the boundary to a very high degree of precision. And it set limits on how much real normal matter, baryons, how many neutrons and protons, and normal matter is only about 4.6%. A follow-up satellite, Planck, in 2013, found that the age was slightly off. It's 13.798 billion years. It's 4.8% baryons, normal matter, 26.8% dark matter, and 68.3% dark energy. And it set some limits on the neutrino content of the universe. And it measured all the parameters, the lambda CDM, the standard cosmology model, not necessarily the right cosmology model, just the standard model, has 8 parameters, and they measured all of them with Planck. And I'll just mention again here that there's another Nobel Prize given to the theory of cosmology. And the first of these 3 people named here, Jim Peebles, is a Canadian. He's from Winnipeg, although he's been at Princeton University for pretty much his entire career. There's what you measure. There's the Planck satellites, result of the measurements of the entire sky after subtracting off the 2.728 degrees. It's not a uniform. This is the part where these are actual, real, high significance measurements. And you can see that there's lots of blobs. And the cosmology theory has to explain what these blobs are and what this all means. And it turns out these are required. These actually fit in the model beautifully. And the sizes of these blobs and how much power there is in each of these tells us something. And you'll notice there's a certain amount of power in the large scale structure, and there's a hotter area here and here and over here. There's a cooler area here and here. So there's some power at the sort of large scale structures, but most of the power we see is in these little tiny dots all over the place. And these actually tell us something. If you take this and try to analyze this, how do you analyze a picture like this? What do you do to make that, get some science out of that? It turns out there's something called the power spectrum, where you look at how much power there is as a function of size. And this is the power spectrum of that picture I just showed you. The top axis here is the scale, it's the size of the blobs. And you can ask how much power is there in a particular size scale. And it turns out that these red data points are what you get. And within the current best theory we have, these peaks mean something. This peak actually gives you the age of the universe. And don't ask me, I'm not a cosmology theorist. I do not know how to do that analysis, but that's what that is. That is the age of the universe. And from where that peak is located, you get this age, 13.798 billion years, if lambda CDM model is right. And at the moment, it's the model. The relative size of these two peaks tells us how much normal baryonic matter there is to how much dark matter there is. Again, I don't know how it's dug deep into the math of the theory, but it's directly measurable. You just make a map of the entire sky at submillimeter wavelengths, where the 3 degree Kelvin is at its brightest, and you get a result like this. And it tells you things about the universe. It gives you confidence in your model because you can get these kinds of things out of it. There are other things we get at submillimeter. Before I leave the science, let me just mention that you can use submillimeter observations to look at galaxies. So here's a bunch of galaxies. Notice this kind of looks like a Planck curve. It's peaks us off the shorter wavelengths, and it tells you something about the temperature of the underlying material in the galaxy. And there are these little lines here, which are the part that are not black body. That's gas atoms or perhaps molecules, but mostly gas atoms that are highly excited. So there are other things that emit besides just hot objects. There are particular features in here, which are useful. In fact, they tell us, lots more about the universe. So just what does it look like? When I say that submillimeter observations are good, here's a picture of a galaxy, standard picture that Centaurus A galaxy that's very popular to take pictures of in normal visible light. If you add submillimeter light and X-rays, the blue is X-rays and the yellow is submillimeter light, you see there's lots more to be seen in this galaxy. So it's just another argument why just having visible light telescopes isn't good. It's not just to do cosmic backgrounds, to do CMB measurements. It's also because there's lots of other science to see. And I'll just and to finish off looking at the science part, the Milky Way in visible light, there's the entire Milky Way in a particular projection in visible light. And here's what it looks like with Planck, which was a submillimeter satellite. And you can see the Milky Way that we saw in visible light mostly through the middle here, but there's all this other structure, most of which is quite close to us. It's within our own galaxy. But out here at the edges beyond when we're looking upwards away from the disk of our galaxy, you're actually seeing the CMB in here and in here. To get the CMB measurements to actually study the cosmic microwave background, we have to really understand all this foreground emission from our own galaxy and subtract it off. And that's the kind of stuff that I actually do in my research a lot. I'm a galactic structure Milky Way person. So there's lots of interesting science in that as well. Okay. There's the science that motivates making a submillimeter telescope. Some of it, really quickly. But again, the title was Very High and Dry. Why very high and dry? It's because the Earth's atmosphere blocks our view of the universe. Now, clouds block the universe. There are things in the air that block the universe. Different things in the atmosphere block the light differently. And this picture sort of shows that. Here is visible light, and visible light coming from space gets to telescopes on the ground. If you go to shorter wavelengths into the ultraviolet or the X-rays or the gamma rays, the atmosphere completely blocks the light. If you go to really long wavelengths, it turns out the ionosphere blocks the light. There's an area where we have radio waves from space get to the ground, but in between, all through the submillimeter, between these two green bars here is a submillimeter, the main thing in our air that blocks the light coming from space is water vapor. There are lots of other things in our air, like nitrogen and oxygen, but those only block very narrow wavelength ranges in general. The thing that really blocks a wide range of wavelengths, especially all through the submillimeter, is water vapor. So if you want to study space from the ground, if you don't want to spend 100 million to $1 billion to go into space, if you want to build a ground-based telescope, you need to try and get above the water vapor, and that's possible to do. So here's our observatory location, the little circle right here in northern Chile. And so let me show you why that's such a good site. And this is the CCAT Observatory. It's in the Atacama Desert. There's a mountain in the Atacama Desert, and we're on top of that mountain, 5,600 meters. This, by the way, is the highest man-made structure on the Earth. And there's what it looks like from space. And our mountain and our site, we share the site with the Tokyo Atacama Observatory, so we're both at the top. They're actually just 41 meters above us, so technically they're the highest man-made structure in the world. We're the second highest, but you'll see more in a few moments. Water vapor, as I said, is the main source of atmospheric problems. It blocks. It also emits. If you look at water vapor in a warm atmosphere, and the atmosphere is relatively warm, it emits. So what happens is that we're trying to look into the universe. We're looking through something that's emitting, which is really quite bright compared to the things we're looking at from beyond the sky, beyond the atmosphere. And the stuff that's beyond the atmosphere is being partially blocked. And so it's like both sides is being messed up by the water vapor. So you really, really want to get the water vapor down. Now, we measure the amount of water vapor by asking if we take all the water above where we are and precipitate it down into a liquid, how much do we get precipitable water vapor? The best site in North America is at Kitt Peak in Arizona, and the number there is around, in these measurements of millimeters of precipitable water, you'll make a column about 20 millimeters of water. One of the other famous astronomy sites is Mauna Kea, and it's about a factor of 10 better. You can get down to about 1 millimeter, occasionally a little bit better. But our CCAT observatory does another factor of almost 10 better than that. Instead of being 1 millimeter, we get down to 0.1 millimeters of water. So there's very little water above us. Now you might ask, what happened? Where's the water? I mean, there's still air. 5.6 kilometers isn't that high. You can breathe at CCAT, although we require people to use full-time oxygen because there isn't that much oxygen. The atmosphere has a scale height for things like nitrogen and oxygen of about 8 kilometers, but water has a much lower scale height. If you go up, the water drops off much faster than the air does because we have rain and snow. The water in the Earth's atmosphere is always dropping out, hitting the ground, and then getting evaporated back up into the atmosphere. And so that process, that dynamic process of water in the atmosphere means that the scale height for water is much lower. And that makes this all possible because we can go, before we run out of any air to breathe, we're running low on, there's very little water. And so that's terrific for us. And here's a very technical slide, but this is just showing how much light gets through from space. So the wavelength here, this is 1 millimeter right here, and to the right, the wavelength scale is in the reverse direction here. So long wavelengths are to the left. All the plots I showed you before had longer wavelengths to the right. So the submillimeter is to the right. And this is showing you the transmission. So up is good. And there are places, wavelengths here around 550 where there's no transmission. This is just, doesn't matter what you do, there's still enough water to block you. And there's another place over here at around 400 microns, which there's no transmission. And these are the best sites in the world. And the best site is the one with the highest transmission is our site at 5612 meters in Chile at Sarachaj-Nator. Mauna Kea site, by contrast, is one that people often consider to be a really good site. That's where I spent 20 years of my career working at Mauna Kea. and it's down here in the green. I did submillimeter astronomy. I'm still doing submillimeter astronomy in Mauna Kea, and this is the best. This is the median. Occasionally gets somewhat better than this, but we do far, far, far better at Sarachaj Natur, which is why we built a telescope there. And there's the site. Now, I showed you something like that in our opening slide with the artist's picture on top. But this is, again, the picture from about 15 years ago. And before we actually started doing anything except site testing. This box here is testing the water vapor above this site. We ran tests here for a couple of years, measuring how much water vapor there was above us, and decided that this was really an incredibly great site to work. Here's the design of the telescope. As designed, this is the design from about 5 years ago, the artist's picture that you saw on the opening slide, superimposed on the photograph I just showed you. And right away, you'll notice it does not look like what you think a telescope should look like. It does not have the big tube sticking out at one side. It's very different. And that's because the optics for this is very special. This is actually a unique telescope. Well, not quite unique because we got such a good design that other people have bought it, and there's been another one built already with the same design, but not as tightly specified as ours. It doesn't work at the same wavelengths. Here's what's special about this telescope in terms of the optical design. We have a large mirror, a 6-meter mirror. And then what's really unusual is that this mirror does not point at a small secondary mirror somewhere. It points at a really large secondary mirror that's off axis here and not blocking the light that's coming in from the sky. The light from the sky is completely unblocked, nothing to bend it, to block it, anything like that. It hits the primary mirror, goes to the secondary mirror, which has to be very large as well. It's actually also about 6 meters in size. And then the light goes from the secondary mirror to a place where we have our instruments, our cameras and spectrometers and things like that. And there's a number of advantages to this. So the main one that really affects us is that it's very, very wide field. This kind of telescope, you can see a large piece of the sky at every instant. And then there are high polarization purity turns out to matter a lot, that we're able to measure the polarization of the light. Tells us a huge amount about the cosmology. The cosmology has very strong predictions about how the light should be polarized. And this makes a great design. So here's what that looks like if you turn that into, combine the two previous slides, the optical design picture and the artist picture of the whole telescope, and you can see the light coming from the sky, coming down and hitting a primary mirror, going over to the secondary mirror, and then into our instrument suite. So this is what CCAT will look like when it's done. It's not quite done yet. I should mention, though, that building a telescope isn't just the telescope. There's a huge amount of infrastructure. Just the road to go up the mountain cost $10 million. We share it with the Tokyo Atacama Observatory, so they're paying half, we're paying half. But it's very difficult to build mountain roads where the mountain is very unstable, constantly sliding down, and you need to make the curves on the road big enough so you can carry huge pieces of material on huge trucks to the top, because we realized that we could not build a telescope from small components at such high altitude. We actually have to build big, big pieces. In fact, we built them in Germany, ship them there, and then we have the problem of getting them up to the top, which means the road has to be really good and wide and everything like that. And I'll show you at least one picture of the road. The site needed to be leveled and foundations dug and all kinds of stuff you need up there. You need power. For example, we generate all our power at low altitude. It turns out at 5,600 meters, there's not as much oxygen as you'd like, and it's hard to generate electricity. There is no power grid. There's no public power grid we can connect to. We have to generate our own electricity. So we don't do that at the bottom of the mountain in the service area. It's still pretty high, where diesel engines are not very efficient. But even at that altitude, it's too high to sleep. So we have a base camp that's a little over an hour's drive away at lower altitude still, 2,400 meters. So every day there's a couple of hours driving just to get up to the observatory at the beginning of the day, and a couple of hours driving at the end of the day to get back to the sleeping place, the base camp. I should just mention that there are a set of instruments for a telescope like this. The starting instruments there's two of them. One that's called CHI, which is a spectrometer being built by our German colleagues. And then there's PrimeCam, which is a 7-element camera. It's a big box like this. The central element which I have to say is the most difficult part of this camera, is the central element. It's a Canadian contribution. So that's what my team here in Canada, I'm part of a team of 14 universities in Canada, many researchers, and we are building PrimeCam central module. It's called PCAM 850. And just to say, the picture doesn't show everything, that last picture. PrimeCam is a big instrument. You can put a small car, but you can put a car inside our camera. So these are big things, but still extremely precise. So you're building really big, high precision optics and electronics and things like that. And it all has to be cooled down to basically superconducting temperatures. So it's a tremendous technology challenge just to build the cameras. I'll mention that our team is very lean. We don't really have the money to have a lot of staff. We're basically a bunch of people in a bunch of universities. So it's a very lean team. We have lots and lots of graduate students, lots of postdocs doing work, as well as some staff. We have about 100 people who are working more or less full time. There's split between Cornell University, which is our major partner in the US, a couple of institutions in Germany. The University of Cologne is the main lead institution in Germany, and in Canada. So there's about 100 people working more or less full-time on this project from the science side, the university-based side. Then there's probably another 400 or 500 people who are contractors or subcontractors who are working on this. So it's a big project. We're not up, I don't think we're up to 1,000 people, but it's a large team of people. There probably was actually 1,000 people involved in this project over the time from when we first did the initial design through the construction. Most of the fabrication people in the factory are now doing other projects, but we still have lots of people. The project office is at Cornell. One of the reasons it's at Cornell is because Fred Young, who donated most of the money for this telescope, is a Cornell alumni. There are directors for the CCAT Observatory who are at Cornell in Canada and Germany, and we have one Chilean director as well. Canada is a 15% partner in this project. There's a science board that decides what science is going to actually be done with the telescope, and that includes a couple of Canadians. We have so many meetings. It's incredible. Of course, they're all on Zoom, except once a year we get together in person, except the very first meeting of these was in April 2020. And as you may remember, that was the beginning of COVID. About a month before that, we all shut down, and I was hosting that first meeting in Waterloo on very short notice, had to change it to a virtual meeting. Had 104 participants showed up for that virtual meeting, but we'd be meeting annually. There was a meeting in Toronto in 2024. We just met recently at Cornell. About half of us were Zoom, participated by Zoom. We've had one meeting in Chile and one in Germany. I think the next one's actually in Germany. So the Canadians involved in this, there are 26 professors in Canada who are part of this project at the moment. Many postdocs and graduate students at 15 Canadian universities. I said 14 earlier. The CCAT project has identified 8 key projects, 3 of which are led by Canadians, which is, we're really doing very well in getting the science leadership in this project, even though, out of proportion to our actual money that we're putting into the project. We're also a major partner in the data center. That's mostly through the University of Toronto and the University of Alberta. There are facility partners who are building the telescope or building the instruments, who are building parts, not just doing the science, but actually building hardware. So those are at Waterloo, Toronto, Alberta, UBC, and Dalhousie here in Canada. And so there's just so many details. I couldn't even start to list them all, but a big part of our money just goes to the telescope company, the company in Germany that's built the telescope and is now assembling it. But that's probably about 2/3 of our telescope costs, and the rest of it is engineering costs that we do with our own design management. It was so much stuff. We're also in Canada responsible for the control system for the entire observatory, and the observatory control system is done from the University of Toronto. The instruments, I mentioned the PrimeCam, and we are responsible for PrimeCam 350. That's the wavelength of PrimeCam. It's the 850 gigahertz central module. We flip back and forth between wavelength and frequency. It's PCAM 350. It's really better to use it. I prefer to use the wavelength measurement there. Where are we today? Well, the current status, it's been a long story. We started designing this in 2017, started manufacturing in 2019. And early this year, we started shipping from Germany the first big parts. Today, the telescope is, all the big parts are assembled on the site. It's not all assembled together, as you'll see in just a moment, but all the big components are done, and it's just a matter really of lifting them up and bolting them into place, and then connecting up various pipes and tubes and conduits inside. So we're very close. The telescope is currently fully funded to what we originally planned, our original budget, but things happen, especially COVID. COVID cost us about $6 million in additional costs, which we partly covered, but we're still looking for some additional funding to finish funding the telescope, which is odd since we're about to be finished building the telescope. We also made a few improvements in the design, which cost a few $1 million here and there as well, which is always a problem, but not unexpected. This is my 5th big project like this, and this always happens, and you plan for it. We do not yet have all the money we need to operate the telescope either, and that is an ongoing thing. We've got about half what we need to run the telescope full time. We really don't want to run the telescope half time, so we are looking for funding partners for the operations. If any of you want to operate a telescope, there's an opportunity. The official opening of the telescope is very soon, April the 9th. That means the telescope will be basically done by April 9th. In fact, it'll all be assembled within the next few weeks. We have work to do to make sure that it works before we actually officially open it, before we have a handoff from the manufacturing team from Germany. Now, I showed you a picture of the site taken more or less from this same spot. The picture I showed you twice before was from 15 years ago. This picture is from a week ago. So you can see there's lots of stuff happening there, but it isn't really clear what it all is. I'll come back in just a moment. That's the picture that I showed you before. You'll notice it's more or less the same place, but things are different. For example, the road that's there in this picture doesn't exist anymore. And of course, all the rocky things that make it not flat have been moved, but there's more to it than that. Here's that same picture again. The telescope is actually right there. You can see it's not quite done. There's also, just for those who are Torontonians, you might notice this thing over here that if you can read carefully, it says BERG on the center of that. That's from Scarborough. We have been having major components built in Canada as well, just separate from everything else. The money that we've sent to build the telescope, some of it's come back to Canada to build major components, such as this box from, this is our cooling system for the telescope. There's a lot of motors that drive the telescope very fast, and they get hot, and we have to cool it. Even though it's very high and it's cool up there, it's not cold enough. The air is too thin. Even if we drove big fans through it, it's still, the air is too thin to cool the engines, all the motors properly. So this picture, as I said, is from about a week ago. Let's look at something more recent. Here's a picture from right down on the site, and this is taken this morning. And you can see this box and this box weren't there in the previous one. So in the last week, we've added on here and here. These are the mirror supports. One is the instrument, one of these is the instrument support. That is, this one on the left is the instrument support, and on the right is the mirror support. The mirrors are not there yet. The mirrors are in these two boxes. This is the secondary mirror, and this is the primary mirror. And in the next week, these will be unboxed and put into the telescope. There's a few other structures here. They are part of the mirror support system as well. And there's also a little elevator that gets put at the end here, and some more entranceway stuff. You can see that there's people working there. There's vehicles. So this was I took this picture at 9:30 this morning with one of the webcams we have on the site. So we're making progress, and we're really, really close. I thought I'd just show you. This is yesterday, a 30-second time lapse. I picked this. It was just perfect because somebody decided to actually test the motors out. So I really like spinning the telescope. So they're doing the crane. They're lifting some stuff in here. But there's the telescope moving. You can see that all the motors work. The telescope moves round and round. So that works. And we're really making enormous progress. 3 weeks ago, there was essentially nothing on the telescope. There was just a basic mount at the bottom. So we're really, really happy with the progress. But there is the future. The professional astronomers in Canada do a plan, a 10-year plan called the Canadian Long Range Plan for Astronomy. It's done by CASCA, the Canadian Astronomical Society, the Professional Astronomy. And this plan last time it came out, the 2021, said that there was a real interest in making a very large submillimeter telescope. And this is a direct quote from that. It calls out CCAT 25, which is a project I've been pushing since 2007. This was our original plan for the CCAT Observatory, but we were not able to get the funding. Actually, Canada came up with the funding for its share of CCAT 25, but the various funding agencies in the US decided not to fund this large telescope. There's also another telescope, a European telescope called ATLAST, which is another large 25 or larger meter submillimeter telescope. And I'm still hoping that we will build CCAT 25. In fact, I've made some provisions. Here's a artist's design of what that would look like on the original site before we did it. The photograph of the original site. It won't go there though because we've just built a telescope there. We built the Fred Young Submillimeter Telescope, which is actually located a little bit to the left of this, but it's in roughly the same area. And where would we build it? Notice this fence. I showed you this. This is the site. I showed you these vehicles from this. This is a picture taken at 9:30 this morning. This is to the right of the site. And I could even go back a few pictures here. Notice to the right, when we were having this flattened, I asked them to flatten this area over here because this is now waiting for a large submillimeter telescope, a 25-meter telescope. I can't see us building this getting started on this before 2035, but this is, I think, the future giant submillimeter telescope. And it's a perfect scientific complement to FYST. The Fred Young Submillimeter Telescope is a survey telescope. It will survey the entire sky every night and find lots and lots of things that we want to look at with a larger telescope to look fainter, to look with finer detail. And this is going to be the follow-up telescope, the telescope where we follow up all the wonderful things we discover with the Fred Young Submillimeter Telescope. And there's just, if you're curious to know what was inside that building I showed you, there's a design. There's lots of technical detail on here. But it's a 25-meter diameter telescope, and that's what it will look like. And I'm afraid that's beyond my career. I've now retired, so I'm only pushing this. I'm not going to lead this project. I'm going to pass this on to somebody a little bit younger than me. So as a summary, we're going to be ready for our first science observations in April. About a few months after that, maybe 4 or 5 months after that, we're going to be able to start actually doing the full science that we have planned for this. It's going to take us a while to test out the first instruments. So the first science observations are making sure those first instruments work. We do have a very good science program now. It's not locked in. We might add some things to it. We're definitely going to make some changes. There's always changes, especially once you start getting data. We are still somewhat understaffed. We're still looking for more people. We're still not fully funded, but we've got some funding sources. And this really provides us, this telescope, the Fred Young Submillimeter Telescope, provides us a stepping stone to the next generation of submillimeter telescopes for 10 years from now. And thank you for your attention. Are there any questions?
That's excellent, Mike. I'm a disembodied voice at the moment, but that's fine. There are some questions which will be coming through on the chat, but as they do, I just wanted to ask you, what do you think was the most difficult part of building this telescope?
Oh, the most difficult part's always getting the funding, convincing people. Okay.
Okay.
So that's, I've done quite a few of these big projects, and it's a lot. It's actually, I'm not saying it quite right, because what really takes time is to develop a concept that you can sell. And it costs money to do the design work. It costs years of engineering work to come up with a design, to come up with a cost. You can't even ask for money until you know what it's going to cost. And you don't know what it's going to cost until you've done the design work. And so I've always found for every one of my big projects, and this is, I've done 5 of these now, that getting the money to actually do the pre-proposal work is actually the hardest thing about the entire project. If you've got I've actually never been turned down for funding for a major science project. For all my instruments have been funded, first time. And it's partly because we've managed to find the money. And I have to thank the University of Waterloo Faculty of Science. I've gone through 3 or 4 deans of science who've been very generous in providing money for me to develop these projects. And several other universities in Canada have been very helpful and had deans. University of Toronto has been very, very, very good. And University of British Columbia has been very, very good at contributing
Uh-huh.
a few $100,000 when I ask, because that's the hardest money to find in these projects. If you've got a really,
Right.
really great design, you've got a great idea, and you're making the best in the world, and literally, this is the best in the world telescope for this kind of science. Best in the world sells.
So hardest thing is to get the money. I mean, we're trying to build a planetarium. I think we all understand that's also pretty hard. So everybody loves the idea, but it is hard to get the money. So you can see some of the questions coming in. What does
I cannot
CCAT?
see the questions. I do
I
not have
will
that.
tell you. What does CCAT stand for?
Oh,
How's that?
CCAT. We don't like to say to talk about what it stands for. We currently call it Sarah Chajnator Atacama Telescope. Okay, because it's on Sarah Chajnator in the Atacama. But originally,
Okay.
our partner was Cornell and Caltech. And so it was called the
Ah,
Cornell Caltech Atacama Telescope. Then Canada and Cologne joined, University of Cologne, and we were going to call it CCCCAT. And we decided that was
okay.
silly. And so we've just,
Needed the power of four.
yeah, well, we did. We had C to the 4th AT at one point, too. We've had lots of
Okay.
crazy names.
Okay. And then fortunately, the benefactor came through and gave the money so you could change the name.
That's right. He put
All
up a
right.
substantial fraction of money. We still put up quite a bit of money in Canada and Germany, but
Mhm.
the largest funding from this is from this alumni donor who's absolutely thrilled with astronomy. And Fred Young shows up at so many of our meetings. He's just great. He's really curious.
Great.
He's just a very active donor. And very gentle and quiet and doesn't not pushy at all. He just comes in and he asks really great questions for somebody who's not an astronomer. And
Right.
it's terrific. Fred's a
Yes.
great, great, great donor. Not just the money. He's interested all the time.
That's great. That's the best kind of relationship.
Yeah.
So a couple more questions here. You mentioned the University of Toronto Professor A. McKellar and the cosmic background radiation. What
Yeah.
was he actually measuring? You want to tell that story?
Oh, so he was he was a molecular astronomer. So in the early
Hmm.
days when we first were realizing that there were molecules in space, he was measuring the properties of the molecules. You want to know what is the excitation temperature? How strongly are these molecules emitting? And
Hmm.
so he looked at I'm forgetting which molecule it was. So I think it was one of the triatomic molecules, slightly larger molecule. It might have been CO2 that he was looking at in space. And he could not find any of these molecules that had a temperature below 2.2 degrees, when what should happen is they should de-excite to lower energy states. There are existing lower energy states in this molecule, and there were so few of them at lower energy states that something was keeping them boosted to 2.2 degrees. And he puzzled about this, and he did not understand why the most molecules should be in their lowest state.
Hmm.
It's like atomic excitation. Atoms de-excite till they're in their ground state. Molecules
Right.
should do the same thing, but the molecules did not de-excite. He looked at molecules, and most of the molecules in space were at 2.2 or hotter than that. There's always a few that have been hit by something, so they heated up for a while and they
Hmm.
de-excite by emitting photons. So he did not know why, but he did measure this number and published it. And that's being realized that was due to the cosmic microwave background.
Aha. Yet another first. That's
Yeah.
great. Um, how does this telescope compare to something like the Vera Rubin Observatory?
Uh, First of all, can I say that Vera Rubin was a good friend of mine?
Yes, you can absolutely say that.
When I was a graduate student, she was a few years older. She'd been working for 4 or 5 years on measuring the dark matter in galaxies. And
Hmm.
I was starting a project measuring the dark matter in our Milky Way. And we ran into each other at a lot of meetings, and she was very encouraging. We used to sit down and compare notes and chat about what it all meant and what dark matter might be and things like that. But the Vera Rubin telescope is a telescope it's a large telescope that's surveying or very deep in space to try and uncover some of these things about what is dark matter and dark energy. And it's just starting right now. So I think it's just started in
Mhm.
the last 6 months, its first observation. So there isn't really any data yet from it.
Mhm.
And it has a very neat design mirror system as well. And a
Mhm.
huge camera, so it can take pictures of an enormous number of objects at one time. But it's one of the sort of the three, leading cosmology visible or near infrared telescopes with the current generation. It's the big one right now.
Right. Yeah, it has just come online. I think we're all really looking forward to it. Okay, so you have this really remote telescope. Presumably you do not sit up there and observe with it. So how do you control it? Or
So
maybe you do. I don't know.
as I mentioned earlier, we in Canada here in Toronto are responsible for the observatory control system, and the guy who's the head of our group, he asked me for what I wanted it to do and how I wanted it to work, and we don't plan to be at the telescope because it's a very difficult environment. You have to have full-time
Mhm.
oxygen. We want to be able to remotely observe. And my instruction to him was I want to be able to observe it from using this telescope from my bed. And he said
Aha.
he has told me at our meeting we had our annual meeting a year ago here in Toronto where we had 100 people, and I was sitting up at the very back of the room and he was down at the front, and he looked up at me across the crowd and said, Mike wants to run this telescope from his bed, and I'm now saying it's possible but only if he has 3 external monitors in bed with him. So yes, we will be remotely observing. We will,
Okay.
most of the time, the telescope will be opened and closed automatically by somebody somewhere far away. We will have day crew go up. We will actually, I don't want to say forbid, but we're really planning on not having people up at the observatory at night. And this
Hmm.
telescope works during the daytime. It's a radio 7 millimeter
You
microwave
don't
telescope.
need to be in the dark. Yeah.
It don't need to be in the
Yeah.
dark. It works much better in the dark because there's less water vapor in the dark.
Oh,
The
fair.
clouds
Okay.
go down, so the sky is generally much better in the night. But there will be days where the night sky, where the day sky is just as good as the night, where we will observe 24 hours a day. And potentially you could be there, but it's a safety issue. We are, at the
Hmm.
moment, the rule is nobody's allowed on the site at night. And
Okay.
so we're forced to observe remotely.
Okay. Well, I mean, it takes some of the romance away, but I do kind of like the idea of doing all the science from my bed. That sounds pretty good. We did have a technical question about your receiver technology. It
Ah,
says, is it heterodyne using sub-millimeter laser or harmonic mixing?
so we use kinetic inductance detectors. So these are very broadband detectors, and it's a really interesting technology. They're kids for short. Um, so they're essentially just bolometers that you tune, and when a photon hits them, um, inductance changes, and we measure the
Okay.
inductance changes on. So every pixel is a separate inductor, and it's a very complicated wiring things, and there's a whole bunch of tuning. Right now, the big problem is how to tune them all properly. So it turns out that's very interesting because it's a very complicated circuit.
Hmm.
And the readout is interesting, but we can make about a detector with about 50,000 of these pixels, and
Wow.
that's just enormous. I'll say that my first started doing submillimeter um, imaging. We had a single pixel detector, 1 pixel, called UKT-14 in Hawaii. And the big
Hmm.
advance was we went to something called SCUBA, which had 31
Right.
detectors, which were really great. But every one of those was a separate handmade detector, and all put together. It was very complicated, and we used it for several years. And then I built SCUBA 2 with a couple of colleagues, and we used something called uh, sorry, I'm drawing a blank on my detector types now. We could build about 4,000 detectors, 4,000 pixels in our detectors. This is age. I've built a bunch of these. I can't think of the name offhand.
Scuba
There's
2,
an acronym for them.
SCUBA2. You can go look it up.
Yeah.
Yeah. Okay. Yeah. So this is a complicated but presumably the process of building them
Well,
has gotten easier with everything
it's a
technological coming
chip, you
along.
know.
Yeah.
The old ones, the original UKT-14 and Scuba were handmade separate pixel detect. Each pixel was separately made. Now we make chips, and we make a
Hmm.
wafer, and the wafer technology is tricky. We have partners in Arizona and Colorado at NIST in Colorado, University of Colorado, who are the fab people. They
Hmm.
fabricate these wafers for us, and then they send them to well, they used to send them to me, but I closed my lab. So they're sending them to our people at Cornell to test them.
Hmm.
And we figure out what's good. We get a couple different varieties of wafers, and then we make another one. And every time we do another version of wafer, it's another couple $100,000 to make the wafer. And we make a few different ways on the same wafer and test out different. We've even just switched from to an aluminum from gold on some of the stuff because it turned out there were some problems with the gold. And there's all
Uh,
this micro machining you have to do on the wafers because they're not finished. Just
hmm.
because you put down all the layers, you still have to do all kinds of cutting and
Hmm.
micro machining on them. So it's a very complicated process, but they are a factor of 20 more sensitive than the current best in the world. The best in the world is my Scuba 2 camera in Hawaii is the best in the world right now. My new camera will be a factor of 20 times more sensitive. Just the camera. The sight is also way better, but the camera itself will be a factor of 20 times more sensitive. And instead of 5,000 pixels, we'll have 50,000 pixels.
So that's incredible. Now, you've talked a lot of just describing this is, sounds like a lot of engineering in your work. Um, but are you going to be looking at the data that this telescope produces? And if
Yeah.
so, what will it look like? It's not going to make pictures, right?
Well, I mean, yeah, we will
Yeah.
at some point have pictures to show, especially depends on which science you're talking about.
Okay.
If you're doing the structure of galaxies and things like that, if you're looking at clusters of galaxies, there'll be some
Hmm.
interesting pictures there. But we're not a really large, I mean, 6 meters is not a huge
No,
telescope.
it's not.
It's really
Yeah.
good for looking at all the foreground stuff in our own Milky Way. But for the distant universe, it's finding things, finding out how big they are to some extent, how big the groupings are, and where they are located and how bright they are. And
Hmm.
that's the cosmology side of it. And also, I did mention briefly the polarization matters a lot too.
Right.
That gives you some really valuable information, especially about neutrinos and
Hmm.
things like that.
Yeah.
We're going to set limits on the neutrino mass, which is something that came out of cosmology, the first cosmology studies, in
It
fact. The first
did
dark,
indeed.
the first dark matter studies set limits on neutrino mass.
Yeah. That's so okay. So it'll come in a mix. There was a question, what will the data look like? So you've given a bit of a description.
It's
Okay,
just a lot
two
of
more.
it's a lot of numbers, and
A lot.
very, it's various plots that I have to ask my postdoc, how to interpret some of the things. He'll
Yeah,
show.
let them do that work. Two more questions that have come in. One is just, was it difficult to get permission from the Chilean government to build this telescope, or are they
Oh,
just, really happy to have people coming down and using their site?
the Chilean government is great. It's complicated. There's so many different regulations we have to follow, and we have to follow the Canadian regulations, the German regulations, the American regulations, and then also the Chilean regulations. This is all about labor
Mhm.
and safety uh,
Yeah.
at one side. There's also access regulations, and also there's you don't want to make a site that looks really bad. They have rules about what you're allowed to do, and it is on indigenous lands. And so
Hmm.
this is also all part of the plan. But there is an area, it's called an astronomy park, and there are probably on the order of 8 or 9 active telescopes within the astronomy park. The astronomy park is mostly, almost exclusively lower altitude than us, of course. We're on the one
Yeah.
mountain that's being used in the
Yeah.
astronomy park. But there's a long history. There's a 30 or 40-year history of very, very good collaboration with our Chilean partners. And I actually meet with a couple of the Chileans who are on our telecon every Monday morning. We have they're part of our technical telecon, and they're on our Tuesday afternoon telecon for science. So
Hmm.
we're working very closely with them, and I think they're leading one of the science. They're leading two of the science key projects. In fact, they're co-leaders on two of them. So yes.
Okay. Um, well, the last question, I think we just have one more come up in the chat, which is, does this research allow us to look at other galaxies and use that to remove more of our own galaxy's emissions to get a better view of the CMB, or is that already, see,
Yeah, we
yeah.
do a better job just using our looking at our own galaxy. The other galaxies that
Mhm.
we see, we'd have to remove our own galaxy because they're, for the most part, our Milky Way is blocking our view of the other galaxies too.
Right. Yeah.
And we get a really pretty good view of our own Milky Way from this. We also, of course, we get to combine all the other work that's being done with other telescopes, and so it's we're getting a really nice picture. But I have to say that this one of the projects I'm most involved with. I'm a little bit involved with some of the dark matter and the cosmology. My main interest is actually in the Milky Way study, and
Mhm.
that's being led by Laura Fussell at Queen's University out in Kingston.
Okay. Wow. Another Canadian thing. Well, the very last question we have is that you said a couple of times, if you're interested in getting involved in the project, let us know. So if somebody wants to know, how can they let you know if they're interested in getting involved in the project?
Yeah, so
You
I
need some
think,
staff, you know. Yeah.
well, we always need staff. We always need, funding for postdocs and students. Um, there there are there are things about doing the science side of this that at some point we're going to be doing some citizen science things because there's
Aha.
so much data. We're going to be getting, many, many, many petabytes every year, and uh,
Okay.
and there will be things that we've just started to identify now. We haven't yet, where we need people to look at the data. We haven't made the tools yet to show the data in ways that people can look for things in it. But we just know that we need more eyes at some point looking at it, and
Okay.
we need some of our clever postdocs to make some better tools for us. We've all, probably a third of my research time is spent writing code. And
That's what it sounds like.
we have postdocs who spend two-thirds of their time or more writing code just to
Hmm.
try and take the data and display it in a different way so we can actually pull something out of it.
Hmm.
And it's, yeah, I'm not sure how I ended up as an astronomer since I had such a strong interest in writing code, but it
Well,
was
it sounds like you're putting it to good use.
I am.
Yeah. Well, so maybe we should all keep an eye out for some citizen science projects that might be coming out of the Fred Young
Yeah.
Submillimeter Telescope in the
About
future.
about a year from now, we'll start getting tons of data, and we won't
Hmm.
know what to do with. We will know what to do with it to start with, but there'll be always so much more to do with it.
Okay. Well, hopefully, Space Place can help you get the word out if there's anything you need some of our enthusiastic, perhaps amateur astronomers or astronomers employed in other areas or people who just have a lot of time on their hands who'd like
Yeah,
to help you out.
I think we should build a control room for FYST at Space Place.
Okay, sounds good to me. We'll put that in the plan. All right. Well, thank you so much. And thank you to everybody who's joined us online and gave us a little bit of slack when we were a bit late getting going. And thanks also to Gabriella and Arvind, who've been in the background helping produce. And of course, biggest thanks to Mike. Thank you so much for sharing your work. It was great to learn about it. And we wish you the best and hope that First Light comes along and brings a wealth of wonderful new data for you to feast on, so to speak.
Great. Well, thank
Thank
you
you
very
so
much.
much. Okay.